Okay, so this is to answer to Beatrice. Because, okay, my notation was perhaps not the clearest one, so I want to clarify what I mean by gradient on the sphere. And you see it more or less from here. So the idea is that here, the way you want to implement this idea that you are on the sphere is via this spherical constraint. And the value, so you solve for this lambda, and this tells you that the lambda that you find is essentially the projection of the gradient on the whole space, so the vector of derivatives with respect to all the components, in the normal direction, and the normal direction is the direction of the vector S itself. So the idea is that when you want to restrict to the sphere, what you have to do is you take the global gradient, let's call it like this, and then you have to subtract the component of the gradient which is in the in the radial direction. And this is what, so if you take the gradient of this function with the Lagrange multiplier, this is what you get, is the original gradient minus the projection in the direction S. So then you know that if you look, so the gradient will be expressed in some basis, but you know that if you look at this object here, the component in the radial direction is 0. So what I can do is I make a change of basis. So I choose this direction to be, I don't know, the last basis vector, and the corresponding component is 0. And the rest of my gradient vector will live in what people call the tangent plane, so the plane which is orthogonal to the normal direction. And this is what I call gradient on the sphere. So it's just an n minus 1 dimensional vector where I got rid of the radial component. Does it make sense? Okay. Okay, so we were here. So we were saying that we have this nice system of linear equation, which is an system of eigenvalue equation. The eigenvector of the matrix M tell me about the stationary points, and the eigenvalue tell me about the energy of the stationary points. And then another quantity that we were interested in was this index, which was controlling the stability of these points. So to look at the stability, we have to look at this Hessian. So let me go back here and take another derivative of this object with respect to another value of S. So I take the double derivative of the landscape with respect to Si, Sj. And what I get is minus m, so this will eliminate this and a factor of S here, which give me back my original matrix M. So this will be minus Mij plus lambda. So if I compute it at S star, this is lambda star. Okay, so now I am assuming that I know the eigenvalues of my matrix M. So I ask, what are the eigenvalues of this Hessian matrix? And I compute it at one particular stationary point, S alpha, whose eigenvalue is lambda alpha. So I know that for S alpha, lambda star takes value lambda alpha. So at S alpha, the eigenvalues of this matrix are minus, is the set minus lambda beta minus lambda alpha for all beta that go from 1 to n. So you are diagonal, this is a matrix plus the identity times a constant. You diagonalize the matrix, and in the basis of eigenvectors, the eigenvalue of this matrix will be given by this. So now you want to understand what is the sign of these eigenvalues. So you will have one mode, one eigenvalue which is 0 whenever you choose beta. Sorry? Yes, this is delta ij, exactly. Sorry, thanks. So you have only one 0 eigenvalue, which is given by this basically spherical constraint that you are imposing. And then you have to count, so for any given alpha, how many of these differences are positive. So now I always mess up, so I have to do it. So lambda beta minus lambda alpha, it will be positive when lambda beta is larger than lambda alpha. So and I have a minus in front. So the number of negative eigenvalues is the number of betas that are larger than the alpha that I'm looking at. So the index, which is the number of negative eigenvalues, will be, if I am not wrong, n minus alpha. Because I'm ordering in this way, so if alpha lives here, all the largest one are in number n minus alpha. Okay, so apart from the zero mode, this tells you that for any values of alpha, these are all saddles, except for one alpha, which is so to have a minimum, I want the index to be 0. I don't want negative eigenvalues, so I have to plug exactly alpha equal to n. And what is the eigenvector which corresponds to alpha equal to n? So I go back here, so I know that the energy of the stationary point is minus the eigenvalue. So the largest eigenvalue corresponds to the smallest energy. So in fact, alpha equal to n is the ground state, which makes sense because it has to be a minimum, because it is the ground state. Yes? No, so here you have, so suppose I'm looking at one particular stationary point, which is labeled by alpha, and it is associated to one given lambda alpha. And then the eigenvalue of the Hessian at that stationary point are summing over all beta, lambda beta minus lambda alpha with a minus in front. So all the betas that are above alpha in my ordering are negative, if the sign is correct, but it should be. And therefore, if I have some negative eigenvalue, the point is a saddle. The only label that gives me no negative eigenvalue is alpha equal to n, which is the ground state, as we want. Okay, so if we have the spectrum, we have the stationary points, we have the energies, we have the index. There was a third property that I will just write to remind it, but we cannot say much about this at this point, and it was the overlap of the stationary point with the signal. Here there is a sign, so okay. It would be plus minus, depending on which sign I choose for S. No, okay, the sign is already inside S alpha, so this would be S alpha dot the signal divided by n. And I cannot tell you much. The only thing that I can tell you is that if you know the eigenvector, then you have to look at how close these eigenvectors are as vectors to the special vector V, and this will tell you where you are on the sphere. Okay, so this is all for fixed realization of the matrix. So for each matrix M, you have a landscape, and you assume that you can diagonalize M, and you have this information. And now the idea is that, of course, you want to do statistics. So to do statistics here means that you want to take the ensemble of matrices M and understand something about the distribution of these eigenvalues, the distribution of this eigenvector, and what is their relationship with V. And this is why now we go back to random matrix theory, because essentially we rephrase the problem again in a problem about spectrum of random matrices. So now I will open a parenthesis on random matrix theory that we will need to go then back to the three questions and try to answer them statistically, if I manage to keep this in my head. Okay. Okay, so let me start here. So now this will be about facts in random matrix theory. And I will consider specifically the type of matrices that you have here, even though some of the things that I will say actually generalize to more general ensembles of matrices, so I will maybe try to specify how this generalize. But let's say for the moment, let me consider again my matrices M, and my matrices M are in fact the sum of a GOE, J, and then I rewrite the matrix which correspond to the signal as R, which was R, and then it was basically a vector times itself transposed, and the vector W now is just my original vector V normalized. So the norm of W is equal to 1. So this type of matrices are, let's say, rank 1 perturbed, or sometimes called spiked GOE matrices. So the GOE part is again in J, and okay, before I introduced J as being a matrix which is taken from this invariant ensemble, but actually these Gaussian matrices have a nice property that they are at the intersection of two ensembles of matrices. So this is both a matrix from an invariant ensemble, and this comes from the fact that the probability of J was proportional to something times the trace of J squared, and this expression here was invariant with respect to rotation, but you understand that you can put here other functions which are not J squared that will be still invariant under rotation. So you can generalize the class of invariant ensembles beyond the Gaussian case. That is what we will consider, and some of the things that I will say actually hold true in general for matrices taken from invariant ensembles, not necessarily Gaussian. And it is also a matrix which is belonging to another class, which is the Wigner ensemble. And when you speak about Wigner matrices, what you mean is that you have matrices symmetric, whose entries are independent, apart from this symmetry constraint, with a distribution that is not necessarily Gaussian, but they have to be independent, and in general, you ask that the second moment is finite, as you have for the Gaussian. Okay, so this is the part for J, and then the part which comes from the signal. So here J is normalized, so that, okay, I will tell this later. So the part coming from the signal is what you call a rank 1 perturbation. So why rank 1? Because essentially is a matrix that you build out of a single vector. It's basically a projection. So if you diagonalize this R here, you will have one eigenvector which is proportional to W, which is actually W because it's well normalized, with eigenvalue R. And then all the others are 0. So you have just one non-zero eigenvalue, and this is why you think of this in a way as a perturbation to the matrix G. It's mostly 0 up to one eigenvalue. And the important point of this is that this R, so this vector W that you choose here, is independent of, so for us is a deterministic vector, but in general it's independent of J in the sense that the distribution of J doesn't know anything about the vector W. And this is a, let's say, you can be more precise about the notion of independence here. So if you want to generalize some of the statements that I will recall, first of all, you can increase the rank of this matrix, so you can add more than one projection, but it's important that the number of projections doesn't scale with n, for what I'm going to say to be true. So you can generalize to finite rank perturbations, where finite means not scaling with n. And also what is important in general is that the piece that you add in here is, as people say in random matrix theory, free with respect to this matrix here. So this, I'm not going into this, but if you look at literature in free probability, you will find generalization of the statements that I'm going to say, which hold true in general when you sum two matrices which satisfy this condition of freeness. But for us, it's simple. It just means that the two terms are independent. Okay, so and my notation is as before, so the eigenvalues are, let's say, ordered. These are the eigenvalues of M. The corresponding eigenvectors are normalized to 1. And whenever I'll write now an average of something, what I mean is in general that I average with respect to the distribution of M, which is basically the distribution of J shifted by some constant, the quantity averaged in the M. Okay? Okay. Okay, so the first thing that you can ask about these matrices is, what are the properties of eigenvalues? And I want to make a distinction so this will be about eigenvalue distribution. And for this discussion, it's somehow useful to make a distinction between what I will call the continuous part of the eigenvalue distribution, so let me call it a density, and eigenvalues which do not belong to the density that I will call isolated eigenvalues or outliers. So to be sketchy, I think one can understand the difference if you think about, let's say, the experiment where you are at finite n, you generate many matrices, you diagonalize them, and for each matrix that you have, you look at the distribution of the eigenvalues on the real axis. The eigenvalues are real because my matrix is symmetric. And at finite n, you will have regions where maybe this eigenvalue are many, so they tend to concentrate. And you may have regions where instead you see that you have only few, or let's say one eigenvalue for my example. So you do an histogram and you should find something like this. So this is not realistic with the number of ticks, but okay. Here you have a region where you have concentration. And concentration in general means that you look at your matrices for different values of n, and you look at what is the spacing between eigenvalues, and you see that the spacing it decreases, of course, when n becomes large, and it is in general of the order of 1 over n. So if I have n sufficiently large and I look at a given interval, little interval of order 1, this is under my normalization of the matrix J, I will have roughly n eigenvalues which lie in this interval. And I may have regions where instead I have only one and there is nothing around, so I call this isolated. Then you increase n. And the idea is that when you have this concentration, you can essentially go to some continuous limit. So you see that this type of histograms will converge to some continuous curve that I will call a density. So at larger n, you will have a much finer structure. Okay, let me draw the density, and then I will pretend that the histogram looks like this. So there is some function that I will call a density, which in principle still depends on n. N here is large, but but is finite. And then if I have my isolated eigenvalue, well, the weight, since I want to normalize this to 1, so the probability should be normalized to 1, this weight will decrease. So I will draw this isolated eigenvalue as a point, and I will call it lambda iso, which can also depend on n, its value. So this is what I call the density. And the idea is that in this regime, the probability that one eigenvalue lies in the interval lambda, lambda più d lambda, is well approximated when n is large by the density times d lambda. Whereas here I have a point and I have to keep the point. Okay. So if I introduce a measure, which is a random measure, actually, which is, if you want the density, or no, the density, I shouldn't say the density because it's just the sum over all my eigenvalues of, let me put a delta function that tells me every time I hit a point where I have an eigenvalue. What I'm saying is that when n is large, for this type of matrices, I can think that in general my density, my measure will be decomposed in two parts. One is the density, which is a continuous function. And then I may have contributions from isolated eigenvalues. So I assume here that there is only one to keep it simple, and I write the corresponding delta function. And now I'd like to say some general things about these quantities and then go specifically to that ensemble of matrices. So for the density, there are many nice things that you can say. And the first thing is that, so if you think, for example, to this GOE and spike GOE, there is, for this quantity, so of course this is random, because these guys are random, so this is random, this is random. But there are nice properties when n becomes large, which correspond to the fact that this function becomes self-averaging. And what I mean is that I take one point, one value of lambda, and I look in some sense at the limit of this random function at that point. So now this is random. And what I find is that if I take n large, essentially this random variable converges to some number. So in principle, at finite n, it is distributed. Nope. But the distribution is such that as I increase n, it becomes more and more peaked around one fixed value. And this fixed value is essentially the average of this quantity that I call like this. And this is what I will call rho infinity. Okay. So if I am thinking about my matrices in the large n limit, in essence, this is telling you that you can, in that limit, forget about averaging and doing statistics. You just take one matrix, you make it large enough, and this will be a good approximation of the rho infinity that you're looking for. And what you're looking for is, of course, this limiting quantity. And one way to get this limiting quantity is using so-called resolvents or Stieltjes transform, which I hope it's written like that. So it's useful if you want rho infinity to introduce another function, let me call it Gn, which is some sort of Laplace transform of this. Well, no, it's a transform of this measure. So it's the integral of this measure divided by z minus lambda. So if I use the expression at finite n of this measure, this will be just the sum over all my eigenvalues of 1 over z minus lambda alpha. Which I can also write. So this is like a trace normalized because it's the sum of diagonal elements of a matrix computed in the corresponding eigenbasis. So let me write it like the trace of an operator, which is 1 over z times the identity minus n. And this is the operator that I call resolvent. Now, this function is useful because it encodes information on the spectrum through divergences, basically. So you see that this function has poles when z is equal to one eigenvalue. So it's singular when z hits precisely, is on the real axis and coincides with one eigenvalue. So to be safe, let me say that I define it away from the spectrum of the matrix M. For example, I can define, so this can be in general a complex variable, so I can define it in 1/2 of the complex plane, let's say C minus. So the space where Z can be written as some real part minus some imaginary part, and then I'll try to analytically continue it going toward the real axis. Okay. Now, the point is that this function here also is well behaved when n goes to infinity in general. So it's also, it has some self-averaging properties. And from the limiting value of this function, you can read off what is the continuous part of the density of eigenvalues. So I will write with the same meaning as here that Gn of Z also has a limit that I will call G infinity. And in this limit, so what happens, all the points which are eigenvalues, so where the density has a delta peak, all the regions where, in fact, these eigenvalues accumulate and become closer and closer to each other, from the point of view of singularity of this function, correspond to the fact that you have poles that accumulate closer and closer to each other, and in the limit, this becomes a branch cut on the real axis. So you have a function that is discontinuous with a branch cut on all the points on the real axis, which correspond to the region where this density is non-zero. So you can formalize this. It's an exercise on the complex plane. And what you can say is that if you know this limiting value of G, then you can use the so-called inverse Stieltjes transform, and you can say that your measure, continuous part, is obtained from this function as the limit, as you approach the real axis, of the imaginary part of this G infinity evaluated at lambda minus eta. So this is just to say that if you know how to compute this object in the limit n large, then you can recover information on the continuous part using this identity. Now this is the density. what should one do to look at isolated eigenvalues? So the idea is that when you have an isolated eigenvalue, you don't have this game of having a continuous limit. There is nothing around it. And in this function here, or you can even look at exactly as it happens in here, the isolated eigenvalue remains there. It remains alone. Here, it remains a delta function with a factor 1 over n in front. And here, you will have a contribution to this function here that is a gain of the order 1 over n times 1 over z minus the isolated eigenvalues. There is nothing around it, so you cannot play this game of introducing a density. So this tells you that if you're interested in understanding what is the value of this isolated eigenvalue, and you know this function gn, what you have to do is to look at 1 over n contributions. So you have to look at 1 over n expansions, if you want, of gn. And these 1 over n terms will have poles. And these poles are precisely at the point where you have an isolated eigenvalue. Yes, so here I'm saying, okay, I imagine that I'm looking at a matrix which admits this decomposition at large n. So you have this region where you have a continuous limit, which is well defined, but you may have regions where you have always only one eigenvalue and nothing around it, so which is gapped, if you want, with respect to the rest. So this region is something that you can really capture in the limit n going to infinity. For example, doing this game. So you really take the limit of this function when n goes to infinity, you do this transformation, and you get the continuous part. Now, any isolated eigenvalue is a bit more tricky because it's away from the region where you have a large n continuous limit. And if you look at this expansion, it will always contribute with something that is of order 1 over n. So it's true at the level of the measure, but it will also be true if you decompose this function here. So you will have the sum over all the eigenvalues which will accumulate, plus contributions of order 1 over n, which of course you do not see when you compute the large n limit. So to pick up them, you have to look at the expansion of this function to order 1 over n. And they will be also singularities because of this structure, but there will not be branch cut. There will be just a pole at that point. Okay, so now what I'd like to say is we go back to matrices of that particular structure, and I'd like to recap basically what is this function. Sorry, the rho in the limit of n large for this spiked GOE. And also, in general, you can ask, so these isolated eigenvalues, if they exist. If you look at finite n, they will take some values, but there is, in general, a limiting value when n is large that I will call lambda iso infinity. So I want to tell you what is this function and what is, when this isolated eigenvalue exists, what is their value for this type of matrices. And then if there is time, I will say something about fluctuations at finite n. Okay? Okay, so maybe I keep this. And I start from this function here. Actually, I start from here. Okay, so now I want to understand what is rho infinity for these matrices. And one way to do this, there are many ways, but one way to do this is to go through this procedure. So you try to compute the resolvent, you take the large n limit, and then you use this formula to get the density of eigenvalues. Now, for these Gaussian matrices, you can compute actually this G infinity. And one way to compute this is to use, for example, the replica method that I will come back to next time. Which I wanted to do here, but there is no time. So if you want to do this calculation, which I think is nice, there is an exercise on this that you find in the links, which is nice because you see all the standard steps of a replica calculation. So what I will do is just to tell you the results of that exercise, and then you can do it if you want. So the first result that you find is that in the Largan limit, which is what you're interested in, your function G infinity, and therefore also rho infinity, will not depend on this perturbation. Again, provided that the rank of the perturbation is small. So if you are interested in the density of eigenvalues at a given point lambda for a matrix which has a spike or a rank 1 perturbation with a given strength R, you find that actually R does not matter when you take the limit and go into infinity, and you just recover the eigenvalue density when R is equal to 0. And this is true also for G infinity, actually. And this maybe is a bit expected because you're taking the limit of n large. R is just one little perturbation with one single eigenvalue, so you do not expect that it will modify a lot this density here. Now, the second thing that you can do with this type of exercise is actually to derive equations for this function here, which are self-consistent equations. Again, in this Gaussian case. So now I have, since I claim that R doesn't matter, I have really a GOE. I don't care about the perturbation. And the type of equation that you get is actually quadratic. So it's of this form. You have sigma square, which perhaps I should recall it. Sigma is the variance of J. So Jij square is sigma square over n, 1 plus delta ij. So you have sigma square g square minus zg plus 1 equal to 0, which for you is an equation for the function g, which you can solve. It is a quadratic equation. You just have to pay a bit attention on the sign that you choose in front of the square root. So I'll give you the right way to write the solution. And then I'll tell you how to justify this. So the solution of this equation, okay, let me go there. Let me call the solution of this equation GSC, which stands for semicircle, and this is obvious in a minute. And this looks something like this. So you have Z minus two sigma squared. So I'm just, so you see, you recognize that you have the square root. I'm just pulling out a value of Z to be okay with the sign in front. And one way you can check that the sign is good is to try to continue this function to the real axis, and so compute it when the argument is real. So you look at G lambda, and lambda is real. And you look at values of lambda being very large. And what you would like is that this function goes to 0 when lambda is large. So you will see that this sign guarantees that this condition is satisfied on both sides, so both for lambda positive and lambda negative. And then if you have this solution, you use the formula that I erased, and you can read what is the asymptotic value of this density, and this is the semicircular law. So this is square root of 4 sigma square minus lambda square, and it is a function that has a precise boundary, so you have to choose sigma because of the square root in the interval minus 2 sigma, 2 sigma. So your density is something that looks like this, is centered in 0, this is 2 sigma, this is minus 2 sigma, and this is rho. And it has these sharp boundaries, so in general, whatever is in here, you call it the bulk of the eigenvalue density, and whatever is really at the boundary, you call it the edge. And this type of shape is more general than the GOE. In particular, if you go to Wigner ensembles, you will find the same asymptotic density, even if the distribution is not exactly Gaussian, but it has a second moment, for example. Okay, so this is the continuous part, and now and it tells you about the density. And now, what about isolated eigenvalues? And I write eigenvalue because the idea is that when you have a perturbation of rank 1, you will in general have only one special eigenvalue that is generated by the perturbation. But in general, you may have more. So to get the expression for the isolated eigenvalue, you have to change a bit the calculation. So this is really n going to infinity. And here, as we saw, you have to look at 1 over n corrections to g infinity. And this is also something that you can do explicitly for this GOE type, and this is another exercise. Which is essentially an exercise where you use the fact that you're taking a large n limit and you know the solution for n going to infinity, and you expand basically around that solution. Now, if you do this exercise, you will find the following results. So the first one is that when r is equal to 0, as I think you expect, there is no isolated eigenvalue. You just have the GOE. You can ask, what is really the limit when n goes to infinity of the largest of my eigenvalues, which I label with n in my notation, and you find that this limit is really equal to this point here, so you are really at the edge, and this is almost surely, so with probability which goes to 1. And if you ask about the smallest one, which I call lambda 1, you will find that this is equal to minus 2 sigma. However, you now switch on R, and this little perturbation does not have an effect on the continuous part, but can have an effect on subleading terms. And in particular, it can generate one of these isolated eigenvalues, of which you can compute the explicit form. So let me take R positive. So if R is positive, what you expect is that if the eigenvalue exists, it will be somehow somewhere away from the region where you have your density that is to the right of your density. If R is negative, you expect it to appear on the left. So when R is positive, then you ask what is now the limit of the maximal eigenvalue. And here you find a transition. So you have a critical value of R, which is, in this case, equal to sigma, which is the variance of the matrix. And if you look at perturbations where R is smaller than the critical value, you see that nothing changes with respect to R equal to 0. So you have really, again, that the maximal eigenvalue sticks to the edge. So it's 2 sigma exactly as it was when R is equal to 0. This is for R smaller. But then if you exceed this threshold, you have a transition. And you have a special eigenvalue, which is pulled out, which you can compute explicitly, and it depends on R and sigma in this way. So for large R, your eigenvalue distribution will have the density, and then you have a point here, which is this lambda infinity. Now, this eigenvalue, the idea is that it appears because you are perturbing the GOE. So if you didn't have the perturbation, you would have nothing like that. Now you're adding this rank 1 perturbation, and you are modifying a bit the spectrum. So the rank 1 perturbation it was of the form R, W, W transform. So what does one expect if one asks about the eigenvector associated to this eigenvalue? So one thing that you can look at is, okay, I take the corresponding eigenvector, which is un. And since this modification to the spectrum is generated by the perturbation, I expect that this eigenvector knows something about the perturbation, so that the overlap with this vector that I'm using to perturb should not be 0 in general. So I look at the square, which is positive. And in fact, what you have is that at the same transition point, things change. So when R is smaller than lambda than R critical, the overlap is 0. And when R is larger than R critical, the overlap is non-zero, and it is increasing like 1 minus sigma over R to the power 2. So when you increase really a lot R, which goes to infinity, you converge towards 1. So you are really, the strongest is R, the more the eigenvector associated to the special eigenvalue aligned with the vector W. Exactly. So here I'm just calling, so in my notation, I had my matrix M was the GOE plus R over N V transpose. And now I call W just V normalized, because so this is the random, and this is the signal. Okay, now I wanted, okay, this is, let's say, a transition on the eigenvector. I wanted to throw a bit of terminology. So first, the first observation that you can make is that when R is equal to 0, the fact that the overlap is 0 is really consistent with the fact that your matrix J is rotational invariant, for the reason that we said before. And what I mean by this is that if r is equal to 0, your matrix J, we say that it has a distribution, a statistics which is independent of W. We fix W, let's choose that it is a given vector, and we say that the eigenvectors of my GOE matrices are like random vector extracted uniformly on the sphere. So if I choose my vector W and I ask what is the typical overlap between a vector that I fixed and a random vector which I choose uniformly on the sphere, I can make this exercise of doing the average and I will find that this is 0. So this is consistent, it's really what I expect. And here this remains true even if R is non-zero, but it is small enough. Now when instead R becomes larger than this threshold, I think one way to interpret this type of transition is if you want to borrow terminologies that come, for example, from quantum mechanics, this is like a localization transition that you have. So in quantum mechanics in general, when you ask about localization, what you have is the wave function that maybe describes your system. So let's assume that W here is my wave function. Then you have some operator and you have a basis which diagonalizes. So quantum mechanics is linear algebra, so it's the same setting. You have a basis which diagonalizes your operator. So let me call this basis U of alpha. And when you say that your wave function localizes in this basis, what you're saying is that your wave function is very close to one vector in this basis and very different from all the other vectors which are orthogonal because you have this orthogonality condition in Hilbert space. And here it's happening the same. So you have your vector W that in a way it's localizing in the basis of eigenvectors of your matrix. You can quantify this, so people when people discuss localization, they usually introduce quantities that they call IPR or inverse participation ratio. So for us, this would be, you have your special vector W, you sum over all the eigenvectors of the matrix this scalar product to the power 4, and then you divide by something that, in our case, is equal to 1 by normalization. And you say that you look at this when n is large, and you say that when this quantity goes to 0, you are delocalized, and when this quantity goes to something which is order 1, you are localized. Now, if I take this as a measure and I try to do it in my case, if I choose R smaller than R critical, I have to estimate what is the typical scaling of each term in this sum. So far I just told you that when n goes to infinity, this scalar product goes to go to 0. But you can actually figure out what is the typical size of the overlap when n is large between two vectors which are random with respect to each other. So first of all, so we discussed a lot this isotropy. So does one expect that the scaling of this overlap will be different for different values of alpha? It will be 0, but it will be 0 essentially for all alpha. So here what I can do is to say that this is one typical overlap with one particular value of alpha, typical, times the number of terms which I'm summing on, which is of the order of n. And now the idea is that, so you find it in the notes if you want to play with this, but you can work out that in this setting, this typical overlap scales like with our normalization scales like 1 over square root of n. So what you have here is a term which is over the 1 over n square, which you multiply by n. So this goes like 1 over n, and in fact, it goes to 0 when n goes to infinity. Now, if you go to this other case, then you expect things to be different, but to be different in one special direction. So I can split this sum between all the alphas that are not equal to n, which is my special eigenvector, plus the term order n, sorry, where alpha is equal to n. Oops. And now the idea is that this is localizing, it's getting very close to this vector. This vector is orthogonal to all the others, so this will be very far away from all the others. So you expect that all the terms in this sum will have the same scaling as above. So you have a factor 1 over n squared here, and then you're summing over n. So this will decay like 1 over n. But this will remain of order 1, because this is what the result is telling you. So not only you see that in the limit n going to infinity, this converges to something of order 1, so you are localized in this sense, but you can also say something more, and this something more is that you have a large sum in principle, which when n is large becomes essentially dominated only by one terms. So all the others one are scaling in a much different way, so they are much, much smaller than this single term. And this, if you want, you can interpret as some sort of condensation. And in fact, for this, let's say, I wanted to mention condensation because if you look, now remember that we are coming from a landscape problem, quadratic on the sphere, so you have an energy. What you can also do is to study the thermodynamics of this problem, so you integrate on your configuration space e to the minus beta times your energy. And you can study this as a function of temperature. And if you do this, you will find transition in temperatures that correspond to this phenomenon of condensation. What you are saying in that case is that it is like here, except that here you are summing over all, if you want, configurations to write down your partition function, and you will have only some which dominate the sum, so you have condensation in this sense. And if you want to look at the thermodynamics, that's another exercise that I have no time to discuss here, but you can find it there, and how this is related to this transition here. Okay, I wanted to say something on fluctuations, but lunch is priority, so I think we start.